Hello, everyone. Welcome to this Open Hardware TV webinar. I'm glad you could join us. We have a very interesting topic today around security and trusted MCUs, TrustZone. We'll have a project and a couple of experts actually from the Open Hardware ecosystem, Abdoulaye Berthe from Low Power Futures and Chris Jones from Crypto Quantique. And they will guide you through the architecture of a project called the Core5 Trusted MCU, an SoC that we're building in 22FDX with our partners and member of Global Foundries, and talk about the issues surrounding security in semiconductor devices and how to enable, and in our opinion, how to leverage open source implementations to enable high security devices. But before I get to that, I'll just provide a very quick overview of the open hardware ecosystem, give you an idea of the growth that we've seen over the last several years and the activity within the ecosystem. And then I'll hand it off to Abdoulaye for his talk and then followed by Chris. At the end of the talk, there'll be about maybe 25 to 30 minutes worth of prepared content that we'll share with you. So at the bottom of the hour, we'll open it up to live Q&A. So please submit some questions in the Q&A tab in the Zoom panel, and we'll do our best to answer those questions for you. But first, we'll get going here, and I'll share my screen with an overview of the open hardware ecosystem. So Open Hardware is a nonprofit organization with a global footprint. We have legal registration as a federally registered nonprofit in Canada and also in Brussels in Europe through our relationship with the Eclipse Foundation, whereby members both from the corporate community or industrial community and academia participate in the development and design verification of open source cores, namely the Core5 family. That's our brand name for the family of open source RISC-V cores. And these range from very tiny embedded class cores, two-stage embedded class cores, right through to larger 64-bit Linux capable, SMP Linux capable 64-bit cores, and everything in between. We're not going to go through the details of the cores in the Core5 roadmap today. There'll be a couple of cores talked about in the SoC that Abdoulaye and Chris will be showing you. But the work that we're doing here is these are system Verilog based cores that are working towards full commercial grade verification using system Verilog UVM verification methods. As I said, we have an international footprint throughout the world in North America, Europe, and Asia. And what the ecosystem is really about is creating an engineering release methodology and development flow whereby we can host open source projects and deliver industry best practices in terms of how that IP is curated, contributed to, verified, and then maintained such that you can trust that IP in a high volume SoC. So from these slides, you can see a whole raft of logos, and we have a number of key industry leaders as part of the industrial membership group. We have quite a few academic institutions that participate and either use the IP, as building blocks in their research or contribute to the IP as well. So it's a very healthy community, and then a really strong partner group that are helping us bring these IP blocks to the industry and support them in the ecosystem. So we're pretty pleased with the level of engagement and participation. And just quickly, the way that the organization is structured is we have a board of directors that the working groups report into, and we have 4 fundamental working groups, two main ones, marketing and technical working groups, and then 2 regional working groups, Open Hardware Asia and Open Hardware Europe, that help to curate and understand local requirements in Europe and Asia and make sure that we have projects that are pertinent to those regions. And one of the projects that is you might be aware of is called Tristan. It's a European Commission funded project. There's 46 different companies that participate in that, and that's under our Open Hardware Europe working group. But the main engine, if you will, of the ecosystem is a technical working group, and there's a series of task groups within that working group. The cores task group obviously looks after the cores, and the verification task group verifies those cores. Then the software and hardware task groups are, if you will, internal customers in the ecosystem that take the cores and build them into systems and or create enabling software around it, be that GCC, LLVM, IDEs, RTOS porting, Linux porting, and so on for the cores. And then in the hardware task group, which is where this Core5 Trusted MCU project resides, that task group builds hardware emulation platforms for the cores, as well as real SoCs that we build with Global Foundries. So you'll hear obviously more about that from Abdoulaye and Chris in a few minutes. And overall, within the ecosystem, with the roughly 103-ish, 104, it keeps growing each week, member organizations that are part of the ecosystem, there's roughly 400 to 500 development engineers that are engaged in some way, shape, or form across, I think we have 23 active projects now within the ecosystem. And that spans the RTL for the cores themselves, the verification, like I said earlier, and then all of the software and hardware enablement. So with that, I'm going to hand it off over to, I'll stop my share and bring it over to Abdoulaye, and he will introduce the Core5 Trusted MCU project and start talking about some of the security issues. Abdoulaye, off to you.
Thanks. Thank you, Rick, for the very good introduction. I'm super excited to be here today to introduce the Core5 Trusted MCU. This is a project that we started back in July last year, I believe, and we've introduced the project to the ecosystem, and we were lucky enough and fortunate enough to have other companies in the ecosystem express their interest. Among those, we have Crypto Quantique, who we are co-leading with the project with today. We live really in a connected world, a world that is very connected with millions of devices, but that has an important shortcoming, and that shortcoming is the lack of security. The situation is getting better nowadays with different initiatives that are defined by HC and other organizations with the goal of taking into account security when designing system. And this is especially important for the type of system that require functional safety, such as in automotive or industrial application. And the Core5 Trusted MCU has been designed really in that context. It is a secure MCU with immutable root of trust, integrated secure element, and advanced cryptographic services that target ASIL-B readiness. The main challenges that we face while building the architecture was to come up with an architecture that is straightforward enough with a very high level of security, while also taking into account the constraint facing the devices, such as the constraint in terms of power, consumptions, and also the constraint in terms of cost of the end devices. As illustrated here, the architecture of the Core5 Trusted MCU is based on a dual core asymmetrical configuration. So which means that it has essentially two different cores, two RISC-V cores. The first one is the CV32 E20 core, which is a secure core, and the other core, the application core, is the RISC-V, is the Core5 CV32 E40S. The smaller core allows for efficient power saving, and the application core implements a certain amount of safety feature for functional safety application. And the two other masters in the architecture are the embedded FPGA presented here and the micro DMA. So these masters are connected to the rest of the system via a tightly coupled data memory interconnect. And on top of the tightly coupled data memory interconnect, we have the TAE firewall. And the role of the firewall is to prevent access to unauthorized memory location. One important aspect is that the TAE firewall here is configured only by the secure core to regulate the access to the rest of the system for the other master in the architecture. And on the top right corner, we have the security engine. This is a security subsystem with root of trust and advanced cryptographic services to ensure security across the system itself. And the security engine, as you could see, include both symmetric and asymmetric cryptographic services. It also include a fully digital physical unclonable function and the coded for quantum-driven identification for both chip identification and also secure key management. As many projects in the ecosystem, the Core5 Trusted MCU is built with members. So we have a couple of members participating in the project, and I've highlighted here the member contributing IP to this system. So Low Power Future is contributing its security engine with root of trust and advanced cryptographic services. Crypto Quantique is contributing its coded, and Quick Logic is contributing its embedded FPGA. This is an expanded view of the interconnects, and as you can see here, the system could be divided in two main subsystems. So the first subsystem illustrated here is the secure subsystem. So this is composed of the CV32E20, which is a secure core, along with the security subsystem, the boot ROM, and a certain amount of SRAM. And the bottom part of the system is the application subsystem. And we've chosen here to isolate the two parts. And the advantage of that is that the lower part of the system do not have the ability to access the upper part of the system, which is a secure part for better secure operation. And another aspect to mention in the architecture, which is very important, is the fact that the CV32E20, which is a secure core, is the one configuring the TAE filter to regulate the access of the other master to the rest of the system. This is an expanded view of the security engine with root of trust and advanced cryptographic services. As you can see, it implements various cryptographic module to cover both symmetric and asymmetric cryptography, hash function, true random number generation. It includes a fully digital physical unclonable function, a key management unit, and a key store. It also includes the quantum-driven identification device from Crypto Quantique. This is a summary of the advanced security feature. As advanced security feature, we have the trusted execution environment, which ensure secure boot, hardware isolation, and integrated secure elements. We also have advanced cryptographic services, which include both symmetric and asymmetric cryptography, and also true random number generation, and a physical unclonable function, and the path for secure key management and chip identification. Here, this is a brief overview of the integrity and reliability feature of the system. So it includes both anti-tampering function, integrity check on the interfaces, and also the register files. It also includes a reliability function inside the application core and also extended across the entire system. And it also includes a system that generates alert when the integrity function or the anti-tampering functions are violated. The main use cases of the trusted MCU are secure boot to make sure that the firmware or the bitstream that are loaded onto the device are trusted and coming from a safe source. Secure JTAG, especially for debugging during the early stages of the life cycle. Secure firmware upgrade when the device is already deployed in the field, and also secure wired and wireless communication. Among the application of the trusted MCU, we have secure element. It could be used as a secure element. It could also be used as a root of trust module. But the main application are really secure MCU, which include secure sensor fusion or secure wireless MCU. This is an overview of the timeline. Most of the architectural work was done last year in Q4. Today we have a lightweight specification, and we started RTL integration and FPGA prototyping. We're expecting to have a first version of the FPGA prototype by the end of April. And we've started also working on UVM verification, where TC has been working on an overall verification plan. So the next steps are RTL to GDS conversion and the development kit. So in Q3, we'll be working on the firmware and prepare for a tape out in late Q3 or early Q4 2023. This is the evaluation platform that I mentioned on the previous slide, and this is based on the Nexus A7. So this, in fact, is a fully digital implementation of the Core5 Trusted MCU, and we intend to have a demo of this device in June during the European RISC-V Summit. So the evaluation platform will include the bitstream, the board support package, and sample software. And if there are people in the audience who are interested in the evaluation platform, please let us know. These are some useful links to know more about the OpenHW Group and the activities that are taking place. I'll now pass it off to Chris to present some detail on some specific use cases of the Core5 Trusted MCU.
Thanks, Abdoulaye. Hi, everyone. Thank you. Great to be here. Really excited. So just let me introduce myself. I'm Chris Jones. I'm Director of Apps here at Crypto Quantique. We're a UK company based out of London, and we've developed some IP and some software, a software platform to ensure the security of a device that's connected to the internet. As Abdoulaye said, it's quite a growth area, connected devices, and we need to make sure, especially with all the legislation that's coming along, that these devices are securely connected to the internet. So what I'm going to do here with my slides is take you through some detail of how we're going to implement the security part that we've just covered lightly. I'm going to go into a little bit more depth. As Abdoulaye said, this is, we're calling it a TEE. I guess there's a few definitions of that, but this is a kind of like an isolated module that is going to handle all the security of the device, and importantly, the secure boot mechanisms, which I'll explain in a little bit more detail. And it also houses some IP that we developed here at Crypto Quantique we call it the QDID. I'll talk about that in some detail a little bit further. The point here is that this is an isolated unit. It sits behind this firewall. The secure boot mechanism is simply for the 32E20, and that kind of then runs the rest of the device if everything is secure. And this has all these different engines in here to allow you to do encryption for various different algorithms. So let me talk about this unit in a little bit more detail. So this is the, we call it a trusted execution unit. And if we go down into this unit, this gives you a little bit more detail of what's inside here. You can see that these FIFOs are here. This is where the SRAM that's shown here will be configured to have a FIFO mechanism. The idea being that you can simply only go through this interface to get access to the secure unit. So you'll be sending commands in through the FIFO interface which will be signed as they're sent in, and then the controller that's in here will check those signatures and verify that they can be executed, and then execute those commands. So there's no, we don't see any delays with these, because the pipe will be going through here to, say, if you're using the AES accelerator, that'll be quickly accelerating the decryption encryption mechanisms and throwing it out through the receive and transmit FIFOs. So we're making sure that this is extremely powerful part of the unit, and you don't expect to see any very little latency and any throttling down. So let's go through this in some more detail. So we've got this isolated firewall, and as Abdoulaye said, it's only configured by the trusted CPU. It configures what the other processors can access in the unit, and also what this TE can access as well. So we've got communication through these FIFOs. There's a command interface and a data interface to make sure you get fast streaming. We've got a secure store up here. We've added this, which is where you would put root keys for security. Now, one of the things we've done with this trusted MCU is make sure that it's as flexible as possible, so that you guys out there can program it and use the different security mechanisms that you wish. If you don't want to use them, that's fine. You can use either the security mechanism using our technology, which includes the QDID, or you could just do a standard key injection yourselves. And that's what this secure store here is doing. So it can be provisioned with your keys, customer keys, and you can have full control over the security of the device. So we try to make it as flexible as possible. It typically would have a UUID. Most MCUs these days have a UUID to give it an identity number that is different from the identity that comes from the QDID, and I'll talk about that in another slide. Of course, we have the boot ROM, so you've got the boot ROM down here. That's going to run that through the boot process of checking its own firmware on the E20, and then I'll take you through that, how that then checks the application firmware that's running on the other RISC-V core. We've got key generation hardware, so the QDID generates cryptographic seeds, and they're put through the ECC, and we generate key pairs, asymmetric key pairs of RSA, maybe ECC, whatever. We've got our AES accelerator, and of course we've got our SHA support for integrity checking. Also in here, we're going to add some technology from other vendors, such as tamper detection mechanisms and side channel attack as well, just to reinforce the security of this element, not simply alone the QDID that I'll talk about and its side channel attack immunity. We'll be added some other features as well. So hopefully that gives you a bit more detail as to what the TE looks like. So over here in the top corner, you saw the QDID. This is our quantum-driven identity IP block. So this is typically what we use to represent it. This pattern, this pixel photo you can see here, this represents our quantum array. So what this does is, this is an IP block that's integrated into the device, and it extracts an identity from the actual die itself, the actual silicon structure of the die. This means that every single die that a QDID is integrated into has a unique identity. This pattern that is allowed to then be used to generate keys. So you can actually have a unique fingerprint in your device, and from that you can create cryptographic keys. And what's important about that is that means that you can prove that this actual piece of silicon owns that identity. That's very important. The great thing is that the identity, the extraction of the identity from the silicon is using a quantum effect. That means it's unforgeable, it's tamper-proof, and it's impossible to counterfeit. It means you don't have to inject keys into the unit, which is great. That means somebody else doesn't know your private keys, like an HSM. Even though an HSM is really secure, it does mean that somebody else knows your private key before it was injected into your device. And then, of course, there was the actual path of how it got into your device. It could have been in the clear as it was programmed in, etc. If you've got this kind of technology, you don't need to inject keys. Unlike other technologies, PUF technologies, we can have multiple keys in here. You could use them for different applications, encrypting data, etc. You just get the keys on demand. You don't store the keys anywhere else. If you want a key to check a signature, you would simply request the seed from the QDID and generate the key from it. So you don't have to store those keys anywhere, which is very important. You don't really want to store your secret keys in flash memory if possible. And that's what the QDID allows you to do. So they're not stored in secure memory. And of course, you have this now unique device identity, which is based on this quantum technology. And it means the device can prove its identity. So that's the basis of the QDID, the real basis of security in a device. There are other PUF technologies out there, but typically they have tended to use peripherals that already exist in a computer or a CPU or a SOC, typically SRAM or flash, and it utilizes some of the features that to create a PUF. In our case, this PUF was designed from the day one to be a secure element, a security device. So it's been designed for security. We don't utilize other technologies. So the identity, basically what you do is you take an identity seed out of the device and you create a cryptographic key pair, and you hash the public key, which you get this 256-bit number, and that is then the quantum identity of the device, which of course it can prove because it has the private key. So that's just giving you an idea of how the identity works. So as Abdoulaye said, we've partitioned the memory of the device so that the secure E20 can actually control the access of the other core. So let me show you how we are planning to do that. So here, this is a bare metal device. So you've gone to stores, you've got a reel of devices, secure MCUs, you pulled it out of the reel and it's a bare metal device. So you've got the boot ROM and the entire flash of the device accessible. What we're proposing is that you have this kind of eFuse configuration register, which is a one-time programmable fuse, and you can program it to have different features. So here you can either have a secure boot. That's two options. You can either have the QDID secure boot, or you can have your very own secure boot if you wish. Maybe you wanted to do a secure boot from your own cryptographic keys. That's fine. That gives you that flexibility. Or if you want the QDID, then you'd blow this fuse. And then there's a firewall control register, which we mentioned, which will control the partitioning. So in bare metal, none of these fuses are blown, and basically you can see the whole of the flash, which is what you'd expect. Maybe start with the unit and do some debugging and some code writing. Now you can then provision the device, of course. So this is if you want to provision the device where you don't actually want to use the secure boot mechanism. So in this case, typically what you would do is you'd put some kind of root key. The manufacturer may do that. Whoever's making the SOC for you, they might put a trusted key in the secure store area that you could use. But in this case, with non-secure boot, you can see the whole flash of the device, and it would be up to you to configure it to do any further security. So that's one option. Next option would be, now you want secure boot, but you want to actually use your own keys for doing that. So in this case, you would actually, you can see here, you'd program your own keys. So you'd have the root key, and then these other keys would possibly be derived off the root key. So you might have some provisioning master key to allow the device to be securely programmed, some keys for encryption, etc. So this is where you would not be using the QDID, and that's absolutely fine. The device can be programmed for that. However, so say now you wanted this device to be really, really secure, and you were going to use our QDID to implement that. So in this case, you would program this bit that would enable the QDID, and immediately what that would do is would enable the secure boot mechanism of the MCU. You would have your root key in there, which would be either you would supply or the manufacturer would supply, and the other keys. But importantly, what that blown bit here would enable is the key from the QDID. So the QDID, is apart from this array of seeds, it also includes a public key. And that means then you would use that public key inside the QDID to verify that your boot mechanism or your boot code was valid and had been signed by a trusted source. So what happens now if you click or blow the QDID fuse is the E20 can only see this bootloader area flash. So you notice it can't see the other areas from the E40, just this boot area. So what will happen now with this fuse blown is when the device boots, it'll go into secure boot and it will verify this bootloader against the key from the QDID. Okay, so that is now blown forever. So once that's done, that fuse is done, this device will always boot using this mechanism. So what will happen then is if it's verified that your bootloader is good and it is being signed correctly, then inside that bootloader, because it's come from a trusted source, that bootloader is then able to control the firewall, and it will then set a bit in the firewall which allow access to the full flash area, where now the E20 can also check the signature of the firmware that's about to be run by the E40. In this case, the E20 would have been possibly holding the E40 in reset and not allow it to run until it's actually verified this firmware that's running in the main flash area. And this mechanism will run every time the device is reset because you've blown those E fuses. So this is the truly secure boot mechanism. And as you can see, we tried to make this flexible as possible so that if you didn't want this particular secure way of booting, then you could use your own keys and use the other methodology. Image verification, for those of you familiar with secure booting, you've probably seen this before. This is just an example, really. So this is what your image would look like that's in the bootloader space that only the E20 can see. Some examples here, so you'd have lengths and offsets here, then you'd have your image, and then it would be signed. It would have been signed by the private key from Crypto Quantique because you're using our boot mechanism. That would have been signed, and that means the device would then run it if the signature was good. The verification process in the boot ROM would be read the image, SHA it, compare, match against the signature here. So you'd SHA this entire length to here. You would get that SHA and you would compare it with the signature. If it was bad, then you've got a boot failure. There are mechanisms to get out of that mode if you wish. That would be dependent on what the final implementation of the CPU is. Does it just sit there in a loop, or does it reset? If it's good, then it will actually jump to the first stage bootloader. Sort of typical sort of secure boot mechanism. So hopefully that gives you an idea of how the trusted boot is expected to operate in a little bit more detail, using both a standard secure boot mechanism or using a secure boot mechanism using the QDID path that's integrated into the SoC. So there I should leave it. And I guess now Rick will be open to questions, I guess.
Thank you, Abdoulaye, and thank you, Chris, for taking us through those topics. You know, we kind of went through stuff, you know, a little bit at a high level and then some drill down, and we came back up again and we did some more drill down. But just as a general concept for folks who might be new, I mean, I think everybody says, yeah, security is good in terms of they think they understand why it's important. But in particular, what does it mean for a device to have a secure root of trust? And why is that important for the kinds of things that, you know, we're deploying all over the place these days with in the IoT space? So, you know, maybe Chris, you can start off with that, and then yeah.
So root of trust, you can kind of boil that down even further to where does security start? What is the basis that just encrypting something or proving identity? Where does that actually come from? What's the lowest common denominator? And it all comes down to identity. So at some point, a device has to prove its identity. A good example is at an airport. How do you do that? So that's a passport, right? So somebody says, who are you? And you say, okay, I'm Chris Jones. And how can you prove that? So you would give them their passport, and they would look at your photograph and then look at you. And that's typically like, that's the root of trust. So they've taken that is a document that has been prepared by, an important agency, British government or whatever. And there's your photo. They've signed it. It's all in some special plastic book, and you look the same. So that's it, that you've proven your identity. Now, how do you do that with the silicon chip? That's the tricky one. So the way we've implemented that is that we provide this seed that is extracted from the actual chip itself. So it's from the crystalline structure of the chip, and we create this fingerprint. So that's great. That's just a number. Not much use as well, same as UID. They're not really very useful. It's just like, I'm number 7, big deal. Right. So what we do in our tech is we then convert that into a key pair. And that means that device can actually say, I am number 7, and then it can be challenged. So externally, you can say, well, okay, you need to prove that you're number 7. So typically, for those of you familiar with encryption, you would send it a command, a code, a nonce, they call it, some random number. And you would say, okay, encrypt that with the private key that represents your identity, and respond. The device encrypts it with its private key, sends that back, and you can then decrypt it with its public key. And if that's good, then you know that device owns that private key. So it is actually the true owner of that identity. So then the question is, well, how did that key get in there? So as I mentioned in my talk, typically they're generated in an HSM, some cryptographic computer, which will generate these random numbers, and it will be injected into the part. But typically then the HSM knows the private key. It's gone through the programming house. You have to trust somebody to put it in there and all that kind of stuff. So with our tech, you don't know what the private key is, because it's created from the crystalline structure. So nobody actually knows what the private key is, which is the really cool thing about it. Nobody knows the private key, only the puff itself. So now that you've got identity, now the device can actually prove who it is, then everything now starts, it begins. So now you can give it stuff like other keys. Yeah. You can then use it to encrypt stuff and start doing encryption, decryption. So then the security builds on top of that.
So let's just go cut you off there for a second. Let's drill a little further into identity, because random number generation and random number generation technology, whether it's Johnson noise from way back in these big cans, that would be random number generators that actually went into gaming machines and all kinds of different products. Historically, fundamentally, not to overuse the term, but at the root of this is really, really solid identity, and the generation of that identity that nobody knows, or that's not tampered. So let's talk about the value, and I'll throw it to Abdoulaye, and I want to come back to you specifically about QDID and the crystalline structure, because I think the viewers have some questions around that. And we've got some more questions queued up in the panel here that we'll get to in a second, but I want to get into the identity aspect. So talk about how important that is, Abdoulaye, when you're trying to create any kind of a trusted environment, the source of and sanctity, if you will, of that identity.
The identity is important. What I'd like to add to what Chris mentioned is that concept of chain, right? The chain of trust. So we want to make sure that everything that to run on a specific device is sort of trusted. And how do we actually prove that? So we usually have a firmware or an FPGA bit stream, for instance, in the case of the Core5 Trusted MCU on the device. And what we really want to avoid is to run something that is not certified. And for that purpose, we need to establish a certain root of trust, and that goes through the boot ROM and an immutable an immutable root of trust based on a kind of key. And in the traditional way, where you would have, for instance, one key obfuscated in hardware available for multiple chips, then you run obviously onto the problem of that key being leaked. That could be a problem. So that is why it is very important to have technologies based on physical unclonable function that could provide a type of fingerprint that is unique for every single chip as part of the root of trust. So, and that obviously solve the problem that I mentioned. When one key is leaked, then it doesn't compromise an entire line of product, and you could have a unique key per device, and only the device that actually was used to during the enrollment is the one that's capable of regenerating the key. So that is important from security perspective, and I think moving forward, that is key, and everything is going to be built on top of that.
Okay, thank you. So we're going to drill into the identity and generating that random pattern that nobody knows more directly. So, a lot of our community in the open source ecosystem, bunch of digital engineers, chip guys, probably not at the fab part of the SoC, just understanding that, hey, here's my RTL, I've got logical equivalents down in my gates, I'm going to shoot a bunch of masks, and every chip will be the same. But wait a minute, now you're telling me that no, every chip's going to be unique, because we're going to have this little part over here that's magically drilling into the quantum effects of the crystalline structure and pulling up some random seed that we can use for keys. How does that work, Chris? Without giving away the kitchen sink or the farm.
It's magic.
Okay.
So what we have, we call it a quantum array. So it's an array of transistors. Typically, the most common one people use is the 64 by 64 array of transistors, and they're just standard CMOS transistors. There's nothing exotic about this technology in that regard. So you've got these array, and then the really cool bit is our IP, which we patented, which is how we read the quantum tunneling currents across the silicon oxide layer of each of those transistors. So that's the cool stuff. So what we do is we measure the tunneling current across each pair of transistors, and then we compare the two, and depending on which is the left transistor or the right transistor, higher or lower, that gives you a 1 or a 0. So that's the quantum tunneling current is dependent on various factors, but one of the key factors is it's dependent on the nanostructures and the arrangement of the atoms across the silicon oxide layer in that particular transistor. So it's directly from a quantum phenomenon. And that gives you a lot of stuff. Now, that means it's not affected by temperature. It's not. It's immune to many of the sort of classic side channel attacks that you get with other puffs that are out there. It's just completely immune. It's not relevant. The whole circuit is differential all the way through. So any glitch kind of attacks are just not seen. So it means it's very, very robust. And that gives you that fingerprint.
Right. Okay. So, all right. So, TrustZone, root of trust is important. We're going to talk about TrustZone soon. So root of trust is important. We've established that, hey, this is a pretty cool tamper-proof identity, base identity mechanism, which is cool. That's going into the Core5 trusted MCU. There's obviously other architectures out there, right? I kind of said TrustZone a second ago. We've got a question about, hey, cool project, but how does this compare to OpenTitan? So I don't know if you guys have spent any time looking at what the cool work that the low risk guys are doing around OpenTitan. So maybe, and I'll throw it over to you first, Abdoulaye, maybe we can talk a little bit about how the Core5 trusted MCU and this architecture that you guys collectively have come up with compares to things like TrustZone and OpenTitan.
Yeah, sure. I'll start with OpenTitan. So the architecture here, the work that we've done here is for secure MCU, and that is where the system is really, really, really great. So it's not just a secure element or a root of trust module that's to be used in another system. So if you're looking for a root of trust module to be integrated into another system, OpenTitan design might be better in the sense that you have a processor and a set of cryptographic function that's encapsulated. But what we're targeting here is really MCUs, secure MCUs, where one of the constraints is obviously the cost. So and this architecture is very suitable for that. And when it comes to TrustZone, as I mentioned, the challenge for us was really to come up with something that ensure a high level of security without being very, very complex, because after all, there's no point in adding a lot of features in the design when software won't be using it, or when it's very difficult for software to really take advantage of it. So I think from that perspective, we succeeded in building something that ensured a very high level of security, and at the same time that is easy to use from software perspective.
Okay, great. Chris, anything to add to those, to the comments of either TrustZone or OpenTitan?
Sure. On the TrustZone side, I mean, TrustZone is popular. People throw it around and say how great it is, but when they come to actually configure a microcontroller to use it, then I've seen a lot of sweating and use of expletives. So yeah, and of course it's to utilize one core and partition in that single core. But in our case, we've completely isolated the secure element side of it with a completely separate core. So you really have a complete partition. There's no join between those two effectively. Whereas with TrustZone, you're kind of sharing the same memory space and having a little bit of hardware to partition it, and it's just so complicated to configure. Whereas in this case, you just got two MCUs, so it's going to be a lot easier to run them both and understand how the security works. Much simpler.
Okay. Just coming back to the OpenTitan, I'll just sort of summarize kind of the fundamental difference. OpenTitan is a secure boot chip, right? Element to put in your system to have a secure boot system. That functionality is inside the MCU, so your MCU boots securely, and the application core that you're running, has been brought up by a trusted execution environment and a secure boot environment, so that you can trust safely trust the execution of your MCU in a critical system. Okay, we've got just about a little less than 10 minutes left. Got a few more questions here in the Q&A panel, and so if you want to get something into these guys, please let me know. Coming back to identity for a second, has your QDID technology been certified externally by any third parties? Or, I mean, you guys say it's great, fantastic, and the world's wonderful, hallelujah, pass the hot sauce kind of thing.
Yeah, so the difficulty we've had there is that the QDID itself is a very small part of the root of trust of a device. So It's really difficult to actually have that particular one element certified. So we've gone as far as we can with just the IP block itself. So we do have PSA level 2 certified ready, it's called. So it means that you can put it into an ARM device or any core, and it will not prevent you getting level 2 above. So that's the certification we've had. We've given it to third-party houses to say, right, go break it. They took the one place we did, they took about 3 months and they still couldn't break it. So we've got reports of how robust it is to side channel attacks. So it has been tested, it's been peer reviewed. by a lot of cryptographers and quantum physicists. So, we're pretty happy with it. The results of all our test chips are great. It's exceeding expectations, certainly on the performance side. So, yeah, we're really excited about it. We really are.
Cool. And, maybe as some of our attendees might already know, the predecessor to this MCU is called the Core5 MCU. It's a single core device. It's not a trusted MCU. And we're taping that out shortly here, and we'll have development kits by the end of the year. The Core5 trusted MCU will also have development kits, and we'll see the development community and have hacker contests and invite folks to try to break it as well, right? So the idea here is to put as much of this in developers' hands and really, when you think about it as an ecosystem or as a community overall, outside the open hardware ecosystem, just in general, as an industry, we, collectively as hardware developers and software and system developers, software developers as well, do the very users that we're trying to serve, we do them a disservice. If my security is better than your security, everybody should have access to top shelf security. That's the only way we'll truly get trusted devices talking to each other that are tamper-proof and be happy about it. Now that's all great motherhood and apple pie. I mean, it's not going to work that way just because we think it should. But that's the intent here, right? To make building secure devices more accessible. So that's what we're trying to do. Let's talk about debug and then trace, right? So it's almost an oxymoron to say we've got debug holes or debug ports, doors, and trace doors that come into the trusted MCU. How do you implement debug and trace? Or just why don't we just stay with debug for now? It's maybe a little bit more of an answer. How do we do that? How do we debug a secure device? Hey, let me in. I want to look around.
Go, Abdoulaye.
One of the work that we're doing right now is defining the overall secure debugging architecture, and that involves essentially for the debugger to authenticate itself to the chip before letting it in. That is a function that's going to be available during the early life cycle stages, and depending on the level of security required, when the device goes into production, that could be completely disabled or could be kept, depending on the level of security that we want to have on the device.
Yeah, and typically it's expected that you can have different levels. So if you want a field engineer to have access to a device, but only certain areas, then he would be given either a token or a key to allow him access to the device, say out in the field, and he could only then view certain things. That would be configured by the customer when they provision the device. So it's going to be very flexible and real powerful as to who can actually get in and who has authority to see what.
Okay, so you kind of think about it as any other trusted resource on the MCU, right? You need to be authenticated as an agent, if you will, that can access the device.
Sure.
What about trace? I mean, trace, sort of by definition, I'll just keep track of everything that's happening. I'll dump all that data into memory, and then I'll just make it available to someone. How do we do that? Not that we're putting any hardware assisted trace in this device right now, but that's coming. I'll
leave that to you, Abdoulaye. That's out of my scope. I'll just protect it.
We can decline to answer, but it's almost an oxymoron. Right?
So I guess the question would be, how do you get the trace really out of a device? Is that the question? Because yeah.
I mean, you're basically turning on something that's allowed to watch everything that's going on, and basically, generate, if you will, a signature of the operating, parameters of the device. You're tracing what's happening, and then in theory, you're dumping that out into the public. In theory,
and that is one of the advantages of the TE filter in the diagram, is that it decide really which one of the masters is going to be able to access the various memory location. So upon authentication, when the debugger is authenticated, we could then allow any other IPs in there to be able to write into some specific memory location or not. So we could always control it from the secure core.
Okay, and would that be the same for any bit stream that gets loaded into the embedded FPGA array from QuickLogic? Like, does that bit stream get authenticated through the TE filter as well before that hardware gets configured?
Yeah, the bit stream gets authenticated. From flash. So the bit stream essentially is in flash along with its signature. So we confirm that the bit stream is trusted before loading it onto the embedded FPGA. Yeah. Perfect.
Well, this is bringing us to the top of the hour. I think we have maybe one more minute or so. So there's a question here about, hey, why are we doing this? You know, is there any legislation in any of the geographies that we're active in, either in North America or in Europe, that is driving some of this work? And the short answer is no. There's certainly legislation that's ongoing. That's not what's driving the work in the ecosystem, I guess, is the answer. This is driven by what the member constituents of the open hardware ecosystem want to work on and develop and enable. And certainly the class of cores in the Core5 family, so the E20 core, very small two-stage core, and the E40 family, 4-stage embedded class core. These are ideal MCU class processors and are being used in production now. A variant of the E40 is in production now. And as we march towards ever increasing IoT device deployment, security is an absolute must. And you can make a strong argument for open source architectures have the opportunity to be the most secure architectures from the standpoint that they're entirely observable. There are no backdoors. Here's the whole RTL for how the SoC is integrated. You can examine, and observe any part of that architecture and design to hopefully produce the most secure devices that the industry can produce together in a collaborative fashion. Like I said earlier, it's a bit of it's a disservice to our end users if Chris's security is better than my security, better than Abdoulaye's security, as an example. If everyone has access to the same high trust secure building blocks, then our intelligent Internet of Things devices will be better for everyone. So, with that, it's noontime here in cloudy Ottawa, Canada. But that's it for our webinar today. Thank you for joining. This will be put online. This episode will be put online for viewing, as we've done with other open hardware TVs. Thank you, Chris and Abdoulaye, for your expertise and your time today. And thank you all for attending. See you next time on Open Hardware TV.